going to talk about his early life, his most popular publication, which is Arithmetica. We're going to do an example of his work and then his mathematic contribution. One more time. All right. So, who is Diophantus? So, he was a Greek mathematician. He was born in Alexandria, Egypt. Little is known about Diophantus, so we don't know the exact year he was born. So it's said that he was born around 200 to 215 AD. This riddle here that I have down here is by another mathematician, Mathematician, and from that riddle, we're going to get the information that he's married with one child. So the riddle reads, "Here lies Diophantus, the wonder behold. Through art algebraic, the stone tells how old. God gave him his boyhood, 1/6 of his life, 1/12 more as youth while riskers grew rife, and then yet 1/7 ere marriage begun. In 5 years there have became a bouncing new son. Alas, the dear child of master and sage. After attaining half the measure of his father's age chill, fate took him. After consoling his fate by the science of numbers for 4 years, he reached his end." So that came from a Greek analogy by Mathematician, and basically that's a book full of mathematic riddles and puzzles. And from that, we got, so it says that he was 1/7 when marriage began. So that is said that he was 26. He had his first kid 5 years after, so he was 31. His son died at 42, and he died at 84. So it's said that he lived about 84 years, but that's the only information about Diophantus' early life that we know. He is known as the father of algebra, that he shares the title with Muhammad Khwarizmi. And there's not much known about his education either, except that we know he stuttered from the Babylonians. And then that was just a picture of where Alexandria, Egypt is. So now we're going to talk about his most published piece. So it's a 13-book series, and it's a collection of him solving determined and undetermined algebraic equations. Only 6 of the 13 books survived. In 1968, 4 Arabic books had popped up, which was translated by Kusta, and we thought that it was the four of the missing books, but it was later found that Costa just used some of the stuff from the Arithmetica. It was said that it wasn't the missing 4, but they did use some of his components from those missing pieces, but it wasn't the exact ones. And then Bombelli was the first to translate it from Greek to Latin in the 16th century, and then Beckett was translated it to Latin in the 17th century, and this became the most famous one. And then if you hit it, here is the book of the series of the this is the 1621 version. Go ahead. Yep. Okay, so he's known as the father of algebra, as I mentioned. The type of equations that he recognized. So he was the first to recognize fractions as numbers, and he used algebraic symbolism. He was the first to use algebraic symbolism before the 15th century. So then he was writing out complete, back then you were writing out complete algebraic synthesis. It wasn't symbols yet, as we learned, but he was the first to start using algebraic symbols. So what we know as X, Y for unknowns, he was using first unknown and second unknown, and then translated that into symbols, and then later on it became X, Y, when we do for the unknowns. He thought negative numbers were useless. So this equation here, we have 4x plus 20 equal 4. So if we subtract 20, that would give us negative 16, making x negative 4. And he thought that that was meaningless because how could you have -4 books? So he didn't like negative numbers at all. He only focused on positive rational numbers. So that takes us to the quadratic equation, which this looks familiar to what we know today. But he had 3 separate versions because 0 wasn't determined during that time. And then again, he didn't use negative numbers. So these were the 3 different equations that he used for the quadratic equations. And then he also solved simultaneous quadratic equations. And that's the example that I'm going to show you today. So Diophantus in his book is a collection of 130 equations that he solved. And he didn't have like a set method. He was literally just solving each equation. And what he did to solve one equation may not have worked for the next equation. It wasn't a generalized formula or statement that he came up with. He literally was just solving problems. So the whole book is about him solving 130 problems. So I'm going to show you, you don't have to go up. I'm going to show you that one. So a simultaneous quadratic expression is when we have 2 unknowns and 2 different expressions. So an example of what he did, we're going to have y plus z is 10. And then we have yz is equal to 9. So Diophantus came up with, this equation. He included a 3rd unknown to help solve this equation. And again, it wasn't a method of how it wasn't expressed what method, how he came up with this equation, because again, he didn't have a set standard of how to solve the equation. So each one he approached differently. So I'm not sure how he came up with this, but it is said that this is the equation he came up with to solve this. So from this, we're going to use our original function, our original equation, excuse me. It's going to be y plus z is equal to 10. From this, I know that y is equal to 10 minus z, and I know that z is equal to 10 minus y. So using this to plug back into here, which is something we're familiar with, he used these 2 equations to find our y and z values. So I'm going to plug in y first. So we have 2x is equal to 10 minus z. So we have 2x is equal to 10 minus 2z. Divide that by 2. We get x is equal to 5 minus z, but remember we're solving for z. So z is equal to 5 minus x. And then we're going to do the same thing, but plug in z this time. So we're going to have 2x is equal to, oh no, I did that. Is equal to y, because we already plugged in y, and now we're going to go minus 10 minus y. So then we get 2x is equal to 2y minus 10, which gives us x is equal to y minus 5. And if we're solved for y, we get that y is equal to y is equal to x plus 5. Okay, so now that I have my z value and I have my x value, he used these 2 to plug into this one. So we have that 9 is equal to y times z, which is equal to x plus 5 times 5 minus x, which is equal to 25 minus x squared. So we have 9 is equal to 25 minus x squared. So then this will be negative 16 is equal to x squared. And then this is x squared equal to 16. And then we have x is equal to 4. And since he wasn't focused on those negative numbers, we don't have to do plus or minus. It would just be that 4. So from 4, I can plug this back into these two equations to figure out what's my x and what's my y value. So I get that z is equal to 1, and I get that y is equal to 9. And if we go back and check, we have 9 plus 1 equals 10, and we have 9 times 1, which is equal to 9. So this is an example of the type of problems that he would solve. And then, okay, we can go to the next one. So here's a quote by Kurt Vogel, and this ties in how he became the first before the 15th century to use algebraic symbolism. So it says, the symbolism that Diophantus introduced for the first time and undoubtedly devised himself provided a short and readily comprehensive means of expressing an equation. Since an abbreviation is also employed for the word equals, Diophantus took a fundamental step from verbal algebra towards symbolic algebra. And then we're going to talk about more of his contributions. So again, in his series, he didn't have a set formula that he created, but because he began the stepping stones, he did have an analysis and a equation named after him. So the Diophantine analysis is the method for solving Diophantine equations. And he wants to find integer solutions to the problem that leads to several unknowns. And the equation is what we know today. Ax plus by is equal to c. And the Diophantine equation, it says that the equation has either no solution, infinite many solutions. And according to his equation, a and b, the greatest common divisor has to divide c. So if we have So we have 3x plus 6y is equal to 29. The greatest common divisor would be 3, but 3 doesn't divide into 29. 3x plus 6y equals 30. This will represent a Diophantine equation because 3, the greatest common divisor of 3 and 6 is 3, and it divides 30. So that's what that equation is telling us. And his influence to other mathematicians. So like I stated, Bombelli was the first in 15th century to translate it to Latin. And he translated it, but he didn't republish it for himself. He just borrowed some of the components for his 3-volume book, L'Algebra, in 1572. And then the most famous, which is Pierre de Fermat, wrote Remarks, Corrections, Solutions, and Generalizations, which is how we came to this methods to reduce that resulted in the Fermat's last theorem.